The question of whether humanity is the only form of intelligent life in the vast cosmos, or merely one of many civilizations that have developed across its endless expanse, is perhaps the most profound inquiry humans can ponder. For generations, philosophers, scientists, and dreamers alike have gazed up at the billions of stars glittering in the night sky and wondered if some of those distant suns might host orbiting worlds not unlike our own, home to complex organisms and cultures reaching toward the heavens. Though belief in extraterrestrial beings has persisted across eras and cultures, only in the modern age have we truly gained the tools and technology to search for such alien life in a scientific manner. The past few decades in particular have seen tremendous advancements in developing methods and equipment to detect exoplanets around nearby stars within our Milky Way galaxy and analyze their properties and environments. Space telescopes like Kepler have pinpointed thousands of planets beyond our solar system. Ground-based observatories wielding powerful spectrographs meticulously measure the chemical makeup of exoplanetary atmospheres. Swarms of tiny interstellar probes equipped with light sails ride the stellar winds toward promising worlds light years away. With an estimated 200 billion stars contained in the Milky Way, and many of those orbited by families of planets as our Sun is, the odds seem high that somewhere out in the galactic neighborhood, on a worn rocky planet or icy moon, organisms have arisen and evolved into forms that think, dream, and ponder the stars. Perhaps some communicate with radio signals or laser beacons, unaware of the faint blue world circling the yellow star half a galaxy away that desperately listens for their call. But space is exceedingly vast, with mind-boggling distances between stars and any residence they may host. Even if the galaxy teems with advanced civilizations, they could easily remain hidden or silent to us. We may just be ships passing in the endless night. Yet, if we can overcome this distance and make contact with an alien intelligence, the implications would be staggering. Detecting extraterrestrial technology, structures, or artifacts, either physically or through transmitted messages, would provide definitive proof we are not alone and completely transform our understanding of ourselves and our role in the universe. We would instantly gain access to knowledge and perspectives shaped by a profoundly different planetary environment and evolutionary history. Exchange of scientific data could leapfrog both our civilizations forward. Trade of culture, art, philosophy, and new modes of thinking would enrich both our societies. Of course, differences between two fully independent biospheres and cultures would undoubtedly lead to difficulties in communication and gaps in mutual understanding as well. But the payoff in elevating both civilizations makes the monumental effort to bridge the interstellar void worthwhile. Perhaps alien intelligences are abundant, but go to great lengths to conceal themselves, avoiding contact with emerging civilizations that may pose a threat. Or they intentionally isolate themselves like monks in a darkened monastery, seeking enlightenment through meditation on the profound mysteries of the cosmos. Maybe superintelligent beings once traversed the galaxy, but have since vanished, leaving only tantalizing ruins on remote worlds. Or life itself may follow such rare and improbable evolutionary pathways that even microbial aliens of the simplest sort only exist on one out of millions of planets. These possibilities and more must be weighed when considering our solitude. If after exhaustive search we find no concrete evidence of extraterrestrial civilizations, it would imply one of the most startling secrets of the cosmos, that against overwhelming odds, only on Earth did the special conditions needed for intelligence to arise actually come together. This would place upon humanity a tremendous responsibility. As the lone known bastion of awareness and culture in the observable universe, it would be our solemn duty to continue that precious flicker, keep exploring the galaxy in case others hide in the darkness, and carry the torch for conscious life itself. We may then need to contemplate that while simple organisms may abound, perhaps technology-wielding civilizations are exceedingly scarce. Some unknown great filter prevents them from advancing very far up the ladder of complexity. If this filter lies in our past, such as the difficulty of life originating or evolving intelligence, then our existence is a triumph and future prospects are bright. But if the filter awaits in our future, like hazards of technological adolescence, then uncertain peril awaits. In that dire case, humanity must come together as never before to overcome this hurdle, that the light of consciousness not be prematurely extinguished in the cosmos. These wonders and existential questions tantalize us, yet definitive answers may long elude even our most powerful telescopes and determined probes into the galaxy. Until the day an alien signal is received in triumph, or exhaustive searchers find only silence, the possibility of cosmic companionship endures. Each night as we study the stars, we can imagine a fellow being on some distant world gazing back, asking the same transcendent questions, and yearning to understand humanity's secret. Of all the profound mysteries that humanity seeks to uncover about the cosmos, few compare to the ultimate question of the universe's destiny. Through observation and theory, physics has peeled back the veil on the origin of existence, revealing how the universe burst into being approximately 13.8 billion years ago, in the epochal event known as the Big Bang. Yet, peering far into the future, the universe's eventual fate remains shrouded in uncertainty. Will the universe continue expanding forever into darkness and cold? Will it stop expanding and reverse course back to a cosmic collapse? Or will expanding space tear the very fabric of the cosmos apart in a cataclysmic Big Rip? Each potential ending implies very different realities for the eons ahead, and which scenario unfolds depends on the full properties of space, matter, and the forces which govern them. Grasping the true fate of the universe stands as one of the most profound challenges physics faces. Currently, observations of distant supernovae indicate that the expansion of space is accelerating, driven by a mysterious repulsive force called dark energy, which makes up 70% of the universe's energy content. If dark energy maintains a constant strength over time, it would lead to every galaxy beyond our local group streaking away from each other into oblivion as the universe expands without bound. The accelerating expansion would grow so rapid that in just 100 billion years, the most distant galaxies would be carried away at speeds faster than light, vanishing from our view forever. As more stars exhaust their fuel and fade, the cosmos would grow darker, colder, and more desolate, approaching a dismal end known as heat death. In this bleak scenario, stars eventually stop forming entirely as the supply of gas required to birth new suns dwindles. Over unimaginable timescales of 10⁻100 years, even black holes evaporate away into nothing through Hawking radiation as the accelerating universe expands. In the farthest future, the universe would become an increasingly sparse sea of elemental particles drifting at inconceivable speeds into eternal darkness, with only feeble, hazy glimpses of the cosmic microwave background left as evidence of the Big Bang that birthed existence so long ago. However, there exist other, more exotic possibilities for the fate of the universe hinging on the nature of dark energy. If dark energy gradually fades in strength over billions of years, the accelerating expansion would slow, perhaps even allowing gravity to eventually overcome it and initiate a collapsing phase. The Big Crunch scenario would see expansion reverse into a cosmic contraction, culminating in all matter and energy crashing back into an infinitely hot, dense state, not unlike the Big Bang in reverse. Some theories even suggest this collapse and rebirth into an expanding phase again could repeat cyclically over time. On the other hand, dark energy may strengthen significantly over cosmic timeframes, overcoming gravity and even the forces that bind matter together. This would result in a big rip, wherein galaxies, stars, and even atoms themselves are torn asunder as space rapidly expands. The fabric of space would be ripped to shreds in this scenario. Nailing down dark energy's properties remains the key to determining which scenario transpires. But it constitutes perhaps the deepest mystery in modern cosmology, its nature completely unknown. Unlocking the ultimate fate therefore requires piecing together dark energy's essence using diverse clues from gravitational waves, precise cosmic distance measurements, maps of large-scale structure, and improved models of quantum gravity. Until physics can decipher dark energy's behavior, imagining the universe's destiny billions or trillions of years from now remains conjecture. An eternally accelerating expansion seems plausible based on current data, but holds profound existential ramifications. If the cosmos has no future except eternal dimming, consciousness and culture of any kind may be finite, restricted to isolated oases in the vastness of space and time. Unless civilizations eventually construct artificially maintained habitats of warmth and light, all life and awareness could ultimately blink out. These grim possibilities make researching dark energy's properties critically important. If it only maintains present strength, radical new physics and technologies may allow future civilizations to withstand an eternally accelerating cosmos. Space itself may have to be reshaped and re-engineered on cosmic scales. There may even be methods to migrate consciousness to higher dimensional planes. Perhaps most fantastically, advanced beings may eventually gain ability to manipulate the parameters of reality itself, changing constants of physics and altering dark energy's nature to bring about a more favorable outcome. Or, hidden realms beyond the observable universe could act as lifeboats, offering sanctuary for civilizations fleeing a dying cosmos. There, fostered by conditions unconceived by present physics, sentience and culture could endure. The full story of existence may extend far beyond our native universe. Whatever dark energy has in store, life holds tenacity and ingenuity that should not be underestimated. The current cosmic horizon may not spell the end, if civilizations make unlocking reality's deepest secrets in nature their guiding purpose. And untold realms beyond our universe could be discovered and mastered. Consciousness may find ways to go on, though the universe itself grows cold, weary, and fades away. Of all the bizarre and mysterious phenomena that populate the cosmos, none capture the imagination quite like black holes. Typically formed from the collapsed remnants of massive stars, these extraordinary objects warp space-time itself into a bottomless pit known as the event horizon, from which not even light can escape. Beyond the horizon, concealed forever from external view, matter plunges into the black hole's nightmarish heart, a point of infinite density known as the singularity, where the known laws of physics catastrophically break down. What unimaginable secrets might these dark monsters that gobble up stars and bend the fabric of reality hold? Untangling their mysteries stands among the most profound challenges physics and astronomy currently face. By their very nature, black holes viciously resist investigation, clenched tightly shut behind their event horizons that permit no light or data to escape. Our telescopes can detect black holes only through indirect means, like witnessing their gravitational influence on nearby stars, or detecting the intense radiation given off by infalling matter spiraling toward their mass. Yet precisely because they possess the universe's most extreme warping of space-time, possibly opening a window onto exotic new physics, black holes represent the best hope for unlocking some of existence's most fundamental secrets. One supreme mystery they may illuminate is resolving the clash between quantum mechanics and general relativity. Quantum theory governs the subatomic domain, while relativity accounts for how mass warps space-time on cosmic scales. But the two frameworks do not properly mesh. At the intense densities inside black holes, quantum properties like particle-wave duality should dominate, whereas relativity holds sway over the immense space-time distortions. Some mechanism must connect and unite these theories into a self-consistent framework of quantum gravity. Observing the processes around black holes offers a potent laboratory for witnessing such quantum gravity effects, which could reveal how to unify these pillars of physics into a single grand theory of reality's workings. Some theories suggest black holes may not possess merely a simple spherical event horizon, but a highly complex internal structure hidden from external eyes. Streamers of spacetime twisted into intricate, beautiful patterns called punctures and folds inside the black hole could transmit information from the interior out into space again in subtle ways. Mapping their gravitational ripples and influences could illuminate the black hole's innards, much as seismic waves provide Earth scientists clues about layers within the planet. The internal structure of black holes may ultimately answer the confounding puzzle of what happens to information swallowed by them. Is it destroyed, scrambled, or could it somehow be reconstructed from careful study of the enigmatic objects? Most fantastically, some cutting-edge physics theories propose our universe itself may exist inside a giant black hole, viewable only from the outside. Our entire reality may resemble a hologram projected around its periphery. Black holes also often occupy an important role in theories of the multiverse, where our universe exists among a vast ensemble of other realities. Powerful black holes may act as portals, warping space-time so intensely as to connect different universes, suggesting the possibility of shortcuts through the cosmic fabric between parallel worlds. Studies of black hole behavior and gravitational wave echoes may provide clues to these shocking hypotheses. Observing them may ultimately reveal our own place in the grand, hidden multiverse. Understanding what occurs within a black hole's hyperdense core remains an even more daunting challenge, as relativity dictates it collapses to a singularity of infinite density, where space-time itself terminates. While inconceivably extreme, some speculate sufficiently advanced civilizations may even learn to harness and survive inside such exotic objects. Some physicists theorize energy densities reaching those within black holes, but access new, higher dimensions of reality, providing a means to escape a dying cosmos. Conceivably, black holes themselves may connect to parallel universes, with passage through a network of Einstein-Rosen bridges. Pioneering civilizations may one day routinely navigate such cosmic wormholes sophisticated civilizations may eventually routinely traverse. Black holes likely also played a pivotal role in shaping the large-scale evolution of our universe. In the first fraction of a second after the Big Bang, fleeting primordial black holes far smaller than stellar remnants may have abounded. Quantum fluctuations leading to their creation may explain how structures in the infinite universe developed. Larger black holes arising later through collapsed stars helped determine how galaxies grew and evolved, with their immense gravity accreting matter into the galactic cores. Quasars, the brightest objects known, which shine as matter spirals into supermassive black holes at galactic centers, provided some first illuminations in the early dark universe. Clearly, black holes stand entwined with the broad history of creation itself. How black holes fully evaporate away through Hawking radiation remains unknown. Microscopic black holes from the dawn of time may be explosively decaying even now throughout the universe. Mapping the emissions from such quantum-scale ephemeral objects before they vanish forever could expose new physics. What might remain afterward, as the last wisps of Hawking radiation fade, is deeply uncertain. Perhaps a microscopic, stable remnant preserves information from its prior existence. Or the black hole may simply dissolve, its entrapped contents released back into the quantum raw materials of the universe through mechanisms still obscure. Ultimately, fathoming the abstruse workings of black holes may expose entirely new layers of reality. Their existence intimates universe-spanning links, higher dimensions, parallel worlds, and new physical laws awaiting revelation by audacious minds. As astrophysics presses forward and quantum gravity's universal code is deciphered, unlocking these objects' deepest enigmas, could profoundly reshape existence's entire cosmic narrative in wondrous ways, illuminating a greater reality of which we are but a tiny part. Of all the substances and forces that shape the cosmos as we observe it, none stands as more elusive and confounding than dark matter. This theoretical material is inferred to comprise over 25% of the universe's total mass energy budget, making it more abundant than ordinary matter by a ratio of nearly 6 to 1. Yet dark matter utterly refuses to interact with light or any particles associated with normal matter in any noticeable way, earning it the dark label. Revealing its identity stands among the most pressing challenges facing physics and astronomy today. Unmasking dark matter's properties could profoundly expand scientific knowledge of the fundamentals of reality. The existence of dark matter is powerfully implied by its substantial gravitational influence on galaxies and larger-scale cosmic structures observed across the universe. Yet it remains completely invisible to any type of electromagnetic observation. Clues like gravitational lensing of background objects by its mass, dynamics of galaxy clusters, and precise measurements of the cosmic microwave background all point to far more mass than telescopes can see. This signifies some form of matter that neither emits nor absorbs light, but exerts gravitational pull. Finding direct proof and understanding dark matter would represent a monumental leap. Many theories speculate on the identity of this spectral material that shapes the large-scale skeleton of the universe. The leading hypothesis proposes dark matter consists of a new, currently unknown subatomic particle, given names like the neutralino or axion, which interacts very weakly with ordinary matter. These particles would only influence the universe through gravity. If such particles are confirmed, it would necessitate an expansion of the standard model of particle physics. Alternatively, more exotic proposals suggest dark matter arises from primordial black holes that pepper space from the Big Bang, or is composed of macroscopic objects like dwarf planets or stellar corpses called machos. There also exist even stranger proposals that dark matter results from modifications to known laws of gravity rather than unseen material. Our current theory of gravity, general relativity, may simply break down over cosmic distances and require revisions that could account for the apparent extra mass. Dark matter's true nature may point toward entirely new realms of the cosmos and reality yet undiscovered by science, such as higher dimensions that subtly influence gravity over vast distances. Theorists have abundant ideas, but only direct detection can provide definitive answers. Experiments hunting for dark matter span the cutting edge of particle physics and astrophysics. Ultra-sensitive instruments buried deep in remote mines, shielded from noise, used xenon or germanium crystals to seek out the slightest recoil when hypothesized dark matter particles interact. Space telescopes like Fermi survey the cosmos for signs of dark matter annihilation in regions like the galactic center. Signatures in cosmic rays from dark matter collisions may be identifiable by balloon or orbiter instruments. Any faint dark matter interactions produce ghosts in vast astronomical imaging surveys, possibly identifiable by advanced computer algorithms. Actually capturing and identifying a verified dark matter particle would stand among the greatest scientific discoveries in history. Not only would it resolve one of physics' longest-standing puzzles, it would open a vast new frontier of knowledge regarding the predominant form of matter in the universe. If dark matter comes from a new particle species, it demonstrates that exotic new physical laws await discovery beyond what scientists currently know. The properties of these new particles would have wholly unknown implications for fundamental physics. Discovery would rapidly spawn an entirely new field of dark matter physics with revolutionary applications. Manipulating these curious substances with novel techniques may enable exotic new technologies, such as compact dark matter energy sources. Dark matter itself could become a resource to be harvested, its gravitational influence harnessed for space travel, terraforming, or engineering megastructures on cosmological scales. Its interaction properties with normal matter could drive as yet unimagined inventions. A confirmed understanding of dark matter may also illuminate mysteries like the earliest moments after the Big Bang, when particles froze out to shape cosmic evolution. If certain theories prove accurate and dark matter consists of primordial black holes or axons, it would reveal much about the universe's first fractions of a second, when even light could not yet stream freely. More speculatively, if dark matter links to higher dimensions or a multiverse, it would wholly reshape humanity's cosmic perspective and the possibilities known to exist for life and mind. Almost certainly, unlocking the secrets of dark matter will profoundly expand scientific knowledge and how physicists perceive existence. Discerning the solution to this confounding, century-old mystery may launch humanity into a cosmos stranger, richer, and filled with more wonder than anyone thought possible when gazing up at the stars. Just as Newtonian gravity gave way to Einstein's relativity, and the atom was revealed to contain whole hidden worlds, dark matter's revelation promises to fundamentally redraw the boundaries of the real, lighting mankind's way as we grapple toward understanding reality's deepest essence. Since the ancient Greek geometers first devised spatial dimensions to describe reality, the notion that the cosmos comprises a three-dimensional existence has persevered, seemingly an immutable fact of life. Points determine zero dimensions, lines 1, flat planes 2, and the familiar depth of space defines three dimensions that can intersect at right angles. Yet provocative new theories in physics now propose that additional spatial dimensions may exist curled up at minuscule size, expanding our conception of the possible. Vindicating the existence of such extra dimensions would profoundly reshape humanity's scientific understanding of reality. The concept of higher dimensions entered speculative mathematical realms as early as the 19th century, but only took hold in physics with the development of string theory. This cutting-edge model interprets subatomic particles not as zero-dimensional points, but as tiny vibrating one-dimensional strings. For the mathematics of string theory to work consistently, the strings must inhabit a spacetime with 6 or 7 extra spatial dimensions, curled up at scales far smaller than quarks. If proven real, these extra dimensions would create vast new landscapes to be explored. Mysteriously, the number and sizes of the extra dimensions radically affects physical properties observed in our ordinary four-dimensional spacetime, including forces like gravity. This suggests all humans ever directly experience is a kind of projected illusion within a greater multidimensional reality. Whole new dimensions could potentially be accessed by physically probing at tiny scales we cannot yet reach, or devising advanced techniques to navigate or unfold them to habitable sizes. Extra dimensions may offer shortcuts through spacetime, or gateways to entirely different physical universes. There may even exist infinite additional dimensions that are dynamically compressed down to sizes far below even a billionth of a meter. This astonishing theoretical construct, called the Calabi-Yau manifold, emerges from the mathematics of string theory to model the additional dimensions. Visualizing these structures proves utterly challenging, but their properties give rise to the observed particles and forces of our standard model of physics. Toppling different Calabi-Yau shaped shifts aspects like symmetry and particle types in our universe, rather like a cosmic kaleidoscope. Mathematically, there seems no reason why only 3 of the total dimensions should have unfurled to macroscopic size, while others remain shrunken. But cosmologists speculate 3 large dimensions may allow for the richest complexity of structure, matter arrangement, and life. Higher dimensional universes might permit only simple uniformity or chaotic disequilibrium. Moreover, quantum fluctuations during cosmic inflation may have randomly, temporarily enlarged only 3 dimensions before the others could likewise expand. If only 1 or 2 dimensions inflated, no complex objects or life could exist. Demonstrating the physical existence of extra dimensions would rank among the most significant discoveries in the history of science, overturning millennia of presumption about reality. Proof may come through particle accelerators like the Large Hadron Collider, probing down to scales of a trillionth of a meter and detecting effects from dimensions curled up at that size. Science could also arise in gravitational wave astronomy, where ripples from the higher dimensional bulk cosmos might pass through. Astrophysical signatures attributable to extra dimensions, like small black holes, may show up in cosmic observations. If extra dimensions prove real, the implications would revolutionize fields from technology to philosophy. Controlling their geometry and physical properties may allow transfiguring spacetime for rapid transport or communication. Mathematicians would explore the structures leading physics to extra dimensions, with geometric principles guiding new discoveries. Philosophically, many would struggle coming to grips with a cosmos far grander than previously conceived. Theological debates about divinity and afterlife may shift with new perspectives on dimensionality. A richer, deeper, fuller understanding of reality itself would emerge. Perhaps most radically, adding spatial dimensions expands the diversity and complexity of potential life. Life forms in higher dimensions would not resemble any conceivable creatures of our spatially limited world. Alien species may already employ more dimensions than we are capable of perceiving. Future civilizations might learn to reshape, sculpt, and engineer the extra dimensions to construct artificial worlds and habitats unfathomable to our three-dimensional outlook. Ultimately, the search for extra hidden dimensions probes the most fundamental question there is: what is reality? Finding entirely new spatial building blocks of the cosmos would mean the true picture stretches far beyond anything we thought possible. Just as microscopes revealed galaxies and bacteria, telescopes showed the breadth of the universe, and particle accelerators uncovered quarks, divulging unseen dimensions would completely redraw the boundaries of existence. Reality, it turns out, may be stranger, richer, and far more grand than humankind ever imagined, while still digging in the mud. Among the most tantalizing of cosmic mysteries, the notion of journeying through time itself has enthralled minds for generations. Mr. Wells popularized the concept in his 1895 novel, The Time Machine, and countless science fiction tales since have played with the intriguing idea. But time travel may, in fact, prove more than mere fiction, and be grounded in exotic properties of space-time laid out in Einstein's theory of general relativity. Traversable wormholes through the cosmic fabric, folds connecting distant places and times, may offer a method to accomplish time travel, though tremendous challenges remain. According to relativity, space-time is a flexible medium that can stretch, compress, and twist. Gravity itself arises from the curvature of space-time due to mass and energy. Matter tells space-time how to curve, and space-time tells matter how to move. This interplay allows for the possibility of wormholes, theoretically passable tunnels through hyperspace connecting vastly separated regions. Enter one mouth, traverse through a higher dimensional nexus, and emerge from the other mouth at a remote location. Using wormholes for time travel requires precisely engineering them to induce closed time-like loops, where world lines double back on themselves across space-time. This might be achieved by taking two wormhole mouths and accelerating one to near light speed, then bringing it back to interact with the static mouth. Thanks to time dilation, clock rates will mismatch between the mouths, enabling passage from one end to the other to traverse backwards in external time. Emerging from the static mouth before entering the moving mouth creates a loop in time. While wormholes appear valid under the mathematics of relativity, stabilizing them to remain navigable proves immensely challenging. Quantum effects at the Planck scale are predicted to induce feedback, causing wormholes to decay before anything can traverse them. Exotic forms of negative mass energy may be necessary to keep wormholes open, forms unknown to current physics. Even a Type E civilization may lack the power to build and sustain a working time machine. Assuming the monumental feat of engineering an accessible wormhole is achieved, journeying through time poses enormous risks and uncertainties. Paradoxes like meeting oneself or killing an ancestor before one's birth loom over time travel, raising deep philosophical puzzles. Even microscopic interactions could drastically alter the unfolding timeline through cascading effects known as the butterfly effect. Without extreme caution, the results of interacting with the past could prove catastrophic. One notion imagines time police that strictly forbid unauthorized travel to protect causality. Time travel also appears to violate several conserved quantities in physics, especially information. Hawking's chronology protection conjecture posits quantum effects will always conspire to prevent time machines for this reason. But some theorists maintain that interactions with the past must simply create self-consistent loops that incorporate any changes into history through a process called the Novikov self-consistency principle. What we think of as recorded history may, in fact, already reflect meddling by past time travelers. If traversable wormholes can be engineered, the implications are extraordinary. Physical artifacts may be brought from the future that offer proof of time travel's veracity and provide advanced technology. Scientists could directly observe events like the Big Bang, the rise of civilization, or the future fate of the cosmos. Time travelers could document critical moments in history or gain personal knowledge from interacting with the past. And the ability to visit any period, even witnessing the end of time itself, grants a profound perspective on existence. But time travel also raises profound ethical concerns and threats. Meddling with past events could have devastating unintended effects that irrevocably alter the present reality. Time travelers may act as mere observers of history, but any interaction threatens appending the known timeline into unrecognizable alternate histories. Even well-meaning attempts to guide the past to avoid catastrophes could go awry and produce worse outcomes. Building in safety factors against changing known events may prove extremely difficult. The dangers of unleashing time travel technology irresponsibly seem severe. More unethically, the capability may be abused to concentrate power and wealth, steal resources, suffer enemies through interference, or wantonly alter history out of misguided motives. Governance of time travel technology will need to enforce strict oversight and transparency. Perhaps only small, precision interactions will be permitted to avoid unintended cascades. Safety and ethical factors in time travel will likely require advanced artificial intelligence assistance as well. Wormholes further offer a shortcut for rapid transit across space, enabling interstellar journeys without the need to approach light speed. Connecting star systems via wormholes may one day drive an advanced civilization's expansion and colonization across the galaxy. Building such cosmic infrastructure will require masters of space-time engineering. Ultimately, conclusively proving time travel possible will require reining in wormholes from abstract theory to practical construction. This immense challenge may await civilizations far more advanced than our own. But if the tremendous barriers standing in the way can be overcome through technology and insight, it would utterly transform the cosmic landscape. Perhaps purposeful manipulation of spacetime for humanity's own trajectory through history may await in the distant future. That is, if events unfold as we think they have. Of all the profound mysteries that humanity seeks to uncover about the cosmos, few compare to the ultimate question of the universe's destiny. Through observation and theory, physics has peeled back the veil on the origin of existence, revealing how the universe burst into being approximately 13.8 billion years ago in the epochal event known as the Big Bang. Yet, peering far into the future, the universe's eventual fate remains shrouded in uncertainty. Will the universe continue expanding forever into darkness and cold? Will it stop expanding and reverse course back to a cosmic collapse? Or will expanding space tear the very fabric of the cosmos apart in a cataclysmic Big Rip? Each potential ending implies very different realities for the eons ahead, and which scenario unfolds depends on the full properties of space, matter, and the forces which govern them. Grasping the true fate of the universe stands as one of the most profound challenges physics faces. Currently, observations of distant supernovae indicate that the expansion of space is accelerating, driven by a mysterious repulsive force called dark energy, which makes up 70% of the universe's energy content. If dark energy maintains a constant strength over time, it would lead to every galaxy beyond our local group streaking away from each other into oblivion as the universe expands without bound. The accelerating expansion would grow so rapid that in just 100 billion years, the most distant galaxies would be carried away at speeds faster than light, vanishing from our view forever. As more stars exhaust their fuel and fade, the cosmos would grow darker, colder, and more desolate, approaching a dismal end known as heat death. In this bleak scenario, stars eventually stop forming entirely as the supply of gas required to birth new suns dwindles. Over unimaginable timescales of 10⁻100 years, even black holes evaporate away into nothing through Hawking radiation as the accelerating universe expands. In the farthest future, the universe would become an increasingly sparse sea of elemental particles drifting at inconceivable speeds into eternal darkness, with only feeble, hazy glimpses of the cosmic microwave background left as evidence of the Big Bang that birthed existence so long ago. However, there exist other, more exotic possibilities for the fate of the universe hinging on the nature of dark energy. If dark energy gradually fades in strength over billions of years, the accelerating expansion would slow, perhaps even allowing gravity to eventually overcome it and initiate a collapsing phase. The Big Crunch scenario would see expansion reverse into a cosmic contraction, culminating in all matter and energy crashing back into an infinitely hot, dense state, not unlike the Big Bang in reverse. Some theories even suggest this collapse and rebirth into an expanding phase again could repeat cyclically over time. On the other hand, dark energy may strengthen significantly over cosmic timeframes, overcoming gravity and even the forces that bind matter together. This would result in a big rip, wherein galaxies, stars, and even atoms themselves are torn asunder as space rapidly expands. The fabric of space would be ripped to shreds in this scenario. Nailing down dark energy's properties remains the key to determining which scenario transpires. But it constitutes perhaps the deepest mystery in modern cosmology, its nature completely unknown. Unlocking the ultimate fate therefore requires piecing together dark energy's essence using diverse clues from gravitational waves, precise cosmic distance measurements, maps of large-scale structure, and improved models of quantum gravity. Until physics can decipher dark energy's behavior, imagining the universe's destiny billions or trillions of years from now remains conjecture. An eternally accelerating expansion seems plausible based on current data, but holds profound existential ramifications. The beginning may involve abstract math and concepts far beyond our cognitive reach. Even superintelligent future AI may find the origin intrinsically inaccessible. Invoking something like a divine being that willed the universe into being centuries ago understandably still holds appeal. Certainly, some notion of a timeless consciousness able to manifest endlessly through diverse forms across the multiverse cannot be logically ruled out as a potential first mover. Mystical traditions across cultures speak of such omnipotent creative ground. But these concepts still beg the question of explaining even God's own origin. The unconditioned source of all remains elusive. Perhaps in some profound sense, existence simply had to be, rather than not be, logically, mathematically, ontologically. Exploring why there is something rather than nothing may ultimately rely less on physics and more on abstract reasoning about the nature of reality itself. Carefully executed thought experiments and deductive logic, seeking the minimally necessary grounds for reality, produce conjecture like the need for qualia-generating observers or self-consistent mathematical structures. But confidence in any particular line of pure reasoning remains low. One audacious idea posits our universe emanates as a whole from an advanced civilization in a separate higher dimension above ours. Perhaps we dwell inside their lab experiment, simulation, or work of creative artistry, our Big Bang authored by intelligent beings rather than arising from impersonal physical laws. Such a scenario may be impossible to conclusively prove, but could explain the feeling that the cosmos contains an encoded meaning or intentionality within its mathematical fabric. Some even entertain panpsychism, where primordial consciousness permeates the quantum foam itself as a basic property of nature, not emerging from material phenomena. Mind-like awareness may exist as a fundamental precursor from which our reality crystallized through material instantiation. Pure abstraction could reach upward to generate concrete manifestation. Clarifying how non-physical qualia relates to physical parameters might illuminate matters like the hard problem of consciousness, while hinting at our link to the absolute source. Ultimately, our ordinary scientific conception of space, time, matter, and energy likely all break down in the context of the unimaginable conditions from which everything first sprang. Phenomena like infinities or quantum uncertainty may point toward a deeper monism where mind and matter merge. Fields and particles might dissolve into vibratory mathematics and flow. Causality may reverse, space invert, and the very distinction between within and without evaporate, delineating the strange, formless landscape where our familiar universe first built up promises to massively expand reality's horizons. Perhaps external reality itself even emerges from within the observer in an act of cosmic cognition or recalling. The mystery of being may hinge intrinsically on the genesis of mind and self-awareness to ponder existence. After all, any supposed knowledge of conditions before the Big Bang relies on mental modeling from our standpoint within the aftermath. The beginning may be not an event, but a thought. We must take care not to limit our conception of fundamental reality too severely by the provincial perspective of one temporary civilization rooted in its particular epoch. The full truth likely towers beyond anything we can currently conceive. But pursuing that unreachable comprehension remains a transcendent challenge, where spacetime, matter, and energy themselves all dissolved away into the quantum nothingness. Insights may yet arise that could reveal entirely new facets of reality, presently veiled. That noble quest sparks the imagination in spirit as nothing else.